Our next speaker is Deng Wang with the story of primordial gravitational waves. Please start.
Okay, thank you. Hello everyone. Today I will talk about the story of primordial gravitational waves and from IFIC University of Valencia. So what are primordial gravitational waves? It's very simple. It's just tensor perturbations of the metric from the very early universe. And as we know, inflation can produce primordial gravitational waves. And there are also other cosmological sources can produce primordial gravitational waves. For example, the cosmic strings and the domain walls. A detection of PGW will give the direct evidence of inflation. And it will also give us some crucial clues of variable or correct quantum gravity, since primordial gravitational waves originates from the quantum fluctuations. So here is the Big Bang singularity. And the quantum vacuum fluctuations will produce the scalar perturbations and tensor perturbations. And shortly after that, these perturbations will be amplified by the so-called inflation era, called the exponential expansion phase in the very early universe. And these modes will exceed the Hubble radius during inflation. And when these modes re-enter the Hubble horizon, they will seize the present-day cosmic structure formation. And here I show primordial gravitational waves behaves like this. It will decay over time. And here I can show its dependence, its scale dependence. And in my model, I consider the two primordial path spectrum. And this is the standard analysis used by the Planck collaboration. And the first one is the primordial scalar path spectrum. It is described by two parameters. The first one is the amplitude, AS, and the second one is the scalar spectral index, NS. And here the K is scale and K star is the tensor is the pivot scale. And here I use same pivot scale for scalar and tensor perturbations. And the second one is the primordial tensor path spectrum. And here AT is the amplitude, and we consider the tensor spectral index and its running NT1 here. The key choice is we consider the second order is also the next leading order inflation consistent relation. And it's easy to see that here the tensor spectral index and its running can act as the function of the tensor to scalar ratio and the spectral index NS. Currently, there are three main probes to test the primordial gravitational waves. And the first one, and is also the most popular one, is the CMB. We can test probe the CMB B modes. Also, the primordial gravitational waves will also contribute to CMB temperature and polarization path spectrum. And the next one is the post-terminal rays. The post-terminal ray can also constrain the primordial gravitational waves. But using the recent data, I found the primordial gravitational waves can't act as a single source for the observed stochastic gravitational wave background. And the third one is the elliptical structure, because primordial gravitational waves can affect the cosmic shear and galaxy clustering spectrum, and the very long wavelengths of the tensor perturbations can have an effect on the scale of galaxy formation, and it can lead to non-zero E and B modes. This is the first theoretical prediction from Cedric and Zaldariaga. They proposed primordial gravitational waves at the CMB modes can be observed in the polarization of the CMB. It's also the CMB mode. Here we focus on the CMB. And the elastic structure and positive array requires more time to detect primordial gravitational waves. And here's the story of at the starting of the story of the observational constraints. And the first one is from WMAP in 2013. They gave the 2 sigma alpha bound under 10⁻² scalar ratio 0.38. And after that, in 2018, the Planck collaboration, they used the PR3 likelihood, observed they give the 2 sigma alpha limit 0.1. We can easily see that the natural inflation and the monomu inflation has been rolled out about 2 sigma level, and actually the cosmological or alpha attractors and the hilltop quartic and the Stravinsky inflation is still favored by data. And the most recent and important one is from the BSAP and KKRA collaboration. By combining BK18 and the BAO from SDSS survey and Planck CMB data, they give the tightest bound, tightest 2 sigma bound upper limit 0.036. And so what is the question? This is very important. And by analyzing the minimal R value of MCNC samples from the BSAP KKRA collaboration, I found the minimal value is about 10 to minus 8. So it's very strange for me. Because this means we have found the primordial gravitational waves. You can see here. By using the CMB alone, or is in combination with the BK18 and the BAO and the recent DESI BAO, it's easy to see that we have found the primordial gravitational waves beyond 5 sigma level. But this is very weird. So, but is this the real finding? I think no. Because there are 2 main reasons. Because MCNC algorithm can't efficiently sample the underlying distribution across many orders of magnitude. For example, 10 to minus 30 to 1 as a linear prior of the tensor to scalar ratio. It's hard to explore the whole parameter space via the step C01. Even if the step is learned to improve the sampling in the code, for example, CosmoVerse. In the above case, when finding a high probability density region, the MCNC algorithm tends to sample around this region and won't be far away from this region. So the small R values can be well sampled. So what is the solution? I think we should use logarithmic prior from the tensor to scalar ratio. And in this figure, we can find the 4 available CMB experiments, including Planck WMAP and ACT here, and SPT, the magenta line, as well as their combination with the BK18 and the DESI BAO observations. We can find they also give the clear contour. And for example, Planck gives at 1 sigma level, Planck gives give the constraint and the tensor to scalar ratio minus 5.5, plus minus 2.5. So this is also very strange. I think here the lower limit, because the data can give lower limit, but if you plot the signal, use the mean value against the data, it will be hard to distinguish it. But I think this is just a fitting problem. The data find the evidence of primordial gravitational waves. And what is the inflationary predictions? I think it's here I just show 5 predictions. The data combination of BK18 Planck and DESI prefers a larger analysis. I think most of you will know that because DESI will shift the Hubble constant to a larger value. And the second one is part of Starobinsky inflation is ruled out. Here you can see the right line. The left point is when the E-force number is 50, and the right point is 60. So the 50 is ruled out, and 60 is still alive. And the third one, the alpha attractors are available for this large parameter space crossing about 9 orders. You can see here, the alpha attractors is very small. And the fourth one is a small part of monomial inflation revives. So you can say here, if the power index is 1 or 2/3, it will revolve within 2 sigma level. And the final one is, I think if my results are true, accurate, this will inspire new exploration of very early universe physics. And so once again, if my results are incorrect, this will be the first direct evidence of inflation. So because inflation predicts the tensor spectral index is smaller than 0. And here I plot the tensor spectral index in log space. You can find it will be smaller than 0. And here I show the Planck constraints. And when fixed NT, the tensor spectral index to 0, we can observe this constraint is tightened by several orders. And also, if we light the left 6 parameters in lambda CM free, we will also observe the similar signal in BK18 data. So below I will, in light of my constraints, I will show 3 spectra. The first one is primordial tensor power spectrum. And the second one is CMB lensing B-mode spectrum. And the final one is an inflationary gravitational wave background. It's an energy spectrum. And the first one, here's the cosmic variance, and the pink band is the CMB scales, and here, this is the 1 sigma, 2 sigma, and 3 sigma constraints and the primordial tensor power spectrum. So it's almost nearly a scale invariant primordial tensor power spectrum because NT is smaller than 0, but very close to 0. And the NT run is consistent with 0 at 1 sigma level. Here is the CMB lensing B-mode spectrum. If plotted the data from BK18, the data will like here, appear here, and so I think it's just a fitting problem. My results are just a fitting results. The final spectrum is the primordial gravitational wave energy spectrum. You can say here is the gravitational wave spectrum spans about 10 orders from CMB frequencies here to gravitational wave observatory frequencies here, about 10 to 2 frequencies. And here will be the LIGO band, but I think LIGO can't observe that. Also, I think current positive array observations and such as net graph, PPTA, EPTA, and IPTA, they can't give a signal of primordial gravitational waves. And also, I think the future BBO will give a better constraint, but I think it's just upper limit. And what is the implication for inflation? And the first one, I think one may think is energy scale. We give this energy scale. You can see that its upper limit is very large. So current, my results shows the GUT scale. GUT physics is allowed within 2 sigma because its GUT scale is about 10 to 16. So I also give the Hubble rate is about 10 to 7. And I also discussed the inflation field excursion is very important to quantum gravity and some theories of the very early universe. And I also discussed the equational state of inflation. And I found its nature is of inflation is quintessence-like, but it's very obvious. And I also I discussed the primordial non-Gaussianity. I didn't show here, but you can find it in my recent paper. And your takeaways also, if my results are incorrect, primordial gravitational waves are detected at beyond 5 sigma confidence level by using Planck, WMAP, SET, and SPT, and BK18 respectively. We also give the first evidence of inflation and that beyond 5 sigma. We discussed the theoretical implications of our results. More works are coming soon. Okay, one more slide. Here are the 5 sigma contours from Planck and its combination with the BK18 and the DESI observations. My 2 recent papers, you can find these plots. And finally, I want to say, I hope everyone can help me to cross-check my results. And I don't make sure this result 100%. Okay, thank you.
So we have a lot of time for questions. Johan?
Thank you for your talk. So if understood correctly, you're claiming that we have a 5 sigma detection for primordial gravitational waves, and that with current CMB data, we are sensitive to a value of the tensor to scalar ratio, which is 10 to the power of minus 10, which is 5 order of magnitude more constraining. That is expected from future CMB experiment. Any optimistic prediction for CMBS4 and other remote polarization experiments is 10 to the power of minus 3. But it seems to me that you're claiming that we are sensitive to values of order of 10 to the power of minus 10 with current data.
Yeah, I know what you. Because I also checked the recent CMB stage 4 and Littlebird and Core on their predictions, and they will reach 10 to minus 3 at this level. But I think currently I can't find any error in my code. So I think
I'm not sure, because when you consider values of the tensor amplitude, which is 10 to the power of minus 30,
yeah,
that would correspond to an amplitude of the primordial spectrum, which is 10 to the power of minus 39 or something, which is very close, I think, to the numerical sensitivity. So you probably should double check what happens with when you ask to Camber class or whatever code you used to calculate those values of the big spectrum, because I'm not sure what's going to happen. That's my suggestion.
Okay, thank you.
Hi. You mentioned that primordial gravitational waves can affect large-scale structures. Can you explain a little bit more how they affect them and how you included that in your BAO measurements?
In the BAO measurements, I think because I just know it can affect the cosmic shear pulse spectrum. Because the small-scale tensor perturbations can affect the ellipticity of a galaxy. it will be a stochasticity from the small-scale tensor deviations. But for BO, I think the effect will be very small. I think I don't know.
So you don't include it in the modeling then? It's just like to break degeneracies that you use BAO?
I think BO can just, in my analysis, it can just shift the Hubble constant to a larger value. It can't give any obvious constraint on the tensor to scalar ratio.
Okay.
Thanks for the talk. And I wonder, besides the log prior of R, do you also use log sampling, MCNT sampling?
Log distribution sampling, I think yes, because I use the prior is logarithmic, and then previous analysis just use linear prior.
I'm not saying about prior, but the sampling.
Just a sampling, I didn't consider it.
Okay, then I think because if you don't consider log sampling, then maybe most of your points will focus on larger number, not the small ones. So I think maybe this should also be considered.
Yeah, I have just something related to that. Yeah, it's a good idea to sample the log of R or log of anything rather than the parameter itself if it varies by so many orders of magnitude. But also I would recommend exploring other samplers than Metropolis Hastings because you do find quite significant differences between these different MCMC samplers. So it'd be good to look into that to confirm what you've done.
Okay, I don't know that, but I will try. Thanks.
Yeah, so just related to what you just mentioned, when you use a log prior on R and you sample linearly in the log space for a parameter, isn't that effectively the same as sampling on the log scale in the linear space?
Yeah, I use the log prior and use the step size is similar to the linear prior.
Yeah, so if you take linear step size in the log space, then it's similar to what.
Okay, I will test that. Okay, thank you.
Yeah, so I think this result might come from this. So if you use linear rather than log, then you might get this result.
Yeah, okay.
So let's thank the speaker again.